So, I want you to look at this carefully, because this forms the basis of all the other examples that we see later. Okay. We are looking at a reaction with two steps: metal losing an electron and forming a species which is normally called as metal plus adsorbed in this literature. Okay. And the metal plus adsorbed, in the second step it goes into solution. So, here I have drawn a picture with spheres representing metal atoms. Okay. This top level represents the surface. The next level is below that. So, the electrode is exposed to the solution. So, solution is on top of this. These metal atoms are not exposed to solution. The top surface atoms are exposed to solution. Okay. Now, if the first step happens at particular rate K1, first step involves the transfer of electron. Okay. So, the K1 we can guess that it is going to depend on the potential. If I give more positive potential, I will pull up or I will remove all the electrons. So, I will drive the reaction in the forward direction. K2 on the other hand, on the left side it is metal plus adsorbed, on the right side it is metal plus solution. Therefore, if I change the potential, K2 will not change. I do not have any reason to expect that the K2 will change. If electron is not involved, if there is no charge transfer, then the rate constant is not going to depend on the potential. Now, let us consider one atom, this particular atom. It loses an electron, we are giving positive potential, the electron is pulled into the metal. We are of course connecting with a potentiostat. Therefore, when you apply a positive potential, that means you are removing the electrons. That goes in, this atom is called now as M plus adsorbed species. It is not an atom anymore, it is an ion. Normally in chemical engineering literature or even in other science literature, if material comes from outside and sits on top, you will call it as adsorbed material. But in this literature, the adsorbed here means it can lose an electron, this is a different species now, and they would call it as adsorbed species. So, keep that in mind. So, here the metal atom, adsorbed metal ion, and the metal ion in solution, if that goes into the solution, that is the second step. So, transfer of an electron resulting in a blue colored ion here, this is the first step. This picture represents the second step. This metal ion has metal adsorbed species has gone into solution, that is called M plus solution. This metal atom now is exposed to the solution. So, this forms a surface. Now, this can lose an electron and become M plus adsorbed, and this can go into solution. This can lose an electron and become N plus adsorbed. We do not think this is going to lose an electron, the surface can lose an electron. Only after this goes, the atom below becomes exposed and that can go into the solution. So, the first step is represented here and the second step is represented here. Now, think about this. Let us say total number of sites available on the surface, okay. That is normally given by the letter capital gamma. Okay. I am going to call theta as fractional surface coverage of M plus adsorbed. So, what I do is I calculate how many such sites are occupied by M plus adsorbed. Okay. What is the total number of sites? That ratio tells us, you can say 30% of the sites are occupied by M plus adsorbed. That means 70% of the sites are metal atoms. Now, the first reaction can proceed only from vacant sites. We call the remaining metal atoms as vacant site. So, a metal atom can become M plus adsorbed. If it is already M plus adsorbed, it can leave, it may stay there or it may leave. If I say this reaction is reversible, then I can say it can take an electron and become metal atom again. But we are not considering that case now, we are considering only a simple forward step for the first step, simple forward step for the second step. That means, once it goes into solution, it is not going to come back again. That is an assumption here. These are only two forward steps. Once we learn how to handle this case, we can derive the expression for reversible reaction, more complicated reactions, and I will show you with examples. So, I want to know what happens to the fractional surface coverage of M plus adsorbed with respect to time. Okay. K1 tells the rate at which the forward reaction can proceed. Forward reaction can proceed when K1 is a finite number, when M species here is available. If all the surface is covered with M plus adsorbed, I will not have any more of the forward reaction, because no vacant metal is available. So, this forward reaction, first reaction rate is given by K1 1 minus theta. Theta tells how much fraction of the surface is covered by M adsorbed, 1 minus theta tells how much of the surface is remaining as M. So, I want to write the reaction here, these are considered as elementary reactions. So, if I know the species and I know the rate constant, I can write the rate of the first reaction is K1 1 minus theta. Rate of the second reaction is going to be K2 theta, right. If theta is 0, that means there is nothing on the surface in the adsorbed metal state, then I cannot have any second reaction. If theta is full, I will expect lot of reaction, lot of the second reaction to happen. Rate of the reaction will be high. Theta here it is between 0 to 1, it does not have units because it is a fractional surface coverage. That means how many sites are available with M adsorbed species, right. That normally will be in moles per centimeter square, divide by total number of sites that are available in moles per centimeter square. So, that means the way we have written, theta does not have any units, but units of gamma is going to be moles per centimeter square, units of K is going to be moles per centimeter square second. Okay. Units of K1 and K2 they will be the same here. Instead, some literature may give K1 as second inverse, and then it will use gamma minus another notation maybe beta. This will be beta, where beta is going to be moles per centimeter. When you read the literature, you have to see how they are defining those terms. Then here instead of d theta, it is going to be d beta by dt. So, instead of having gamma d theta by dt, I might write it as d beta by dt, it is going to be K1 gamma minus beta minus K2 beta. It is just a different notation, the way you define this. What we have written here, that equation, we call it as mass balance equation. Here we are assuming certain things. We assume mass transfer is fast. We assume that the model here, we are going to make an assumption K1 is going to be written as K1 e power B1 e, it is exponentially dependent on potential. We are assuming that Langmuir isotherm model works here. That means, if I have M adsorbed here, what is the probability that this atom will lose an electron and will become M adsorbed? We have a number. What is the probability that another atom which is far away, that will lose an electron and become an M adsorbed? We assume that they are all the same. They are not dependent on whether the neighboring site is already M adsorbed or not. So, there is no interaction between the species, that is one assumption. We assume all sites are equal, that is we do not think 1% on this row is more likely to lose an electron compared to the 1% on this row. This in pictorial I am telling you that this one row another row, we are saying all of them have equal energy levels. If they have different energy levels, you will have to use another isotherm called Temkin isotherm. If we think there are interactions, means presence of one species can help or hinder formation of same species or different species, we will use what is called Frumkin isotherm with interaction parameter. If it is positive or negative, it is going to say that it is more likely to happen, less likely to happen, etc. But for simplification, we are going to say this is Langmuir isotherm. Now, if we say it is under steady state, that means the fractional surface coverage of theta is independent of time. You would expect steady state if you do not apply any potential and if the solution concentration other things remain the same, or you apply constant potential, wait for sufficient time, system reaches a steady state, then I can say d theta by dt is 0, it is not varying with time. Then I am going to call that K1 at that DC potential as K1 DC, that is K1 0 e power B1 e DC. We have applied a DC potential, it may be 0, in which case we are not applying any potential. It may be a fixed number, non-zero number, and we wait for enough time, we will get a stable current and we will get a stable surface coverage. If we change the DC potential, go to another value, wait for enough time, I will get another surface coverage and another current value. So, at this condition, I can set this to 0 and I will call the K1 as K1 DC, which corresponds to that specific DC potential, and I will call the theta fractional surface coverage as theta SS to indicate its steady state. We have done this before in Langmuir isotherm model, not in this course, but you would have done it in perhaps chemistry course. Okay. You can rearrange this and get the steady state value of theta SS. I would like you to actually do that. You can see it in the PPT, yes, everything is correct, but why not try this? It is not that difficult. So, I would like you to start with this, try this, get a value of theta SS in terms of K1 and K2, K1 DC and K2. The reason is, next we are going to look at this and say this is the steady state current. Next I am going to tell you how to calculate the impedance. It is a lot easier if you actually try this, learn the steps, then we will go through one or two more types of reactions, maybe not today, subsequent few classes. Once you try it and then get this, it will be a lot easier for you to look at a new mechanism and do this. If you see it in the PPT here, you will feel that you have learnt it, but you may or may not have learnt it well. So, calculate the value of theta SS, it is very simple rearrangement, and you would get K1 DC by K1 DC plus K2. Now, I want you to guess, K2 is a constant, K1 is going to increase when I increase the DC potential. When K1 is a very small value, what will happen to theta? It will tend towards 0. If K1 is a very large value, theta will tend towards, it will not tend towards infinity, it will tend towards 1. So, it makes sense, fractional surface coverage has to be between 0 to 1, and it will go to 0 when you go to very negative potentials. Of course, we are assuming that the reverse reaction is not possible. When you go to negative potentials, you cannot assume that. Even when you go to 0 potential, you have to assume that reverse is possible. If you are in the very positive potential, then you can neglect the reverse reaction, because you are just going to take out all the electrons, it is not going to come back to the M species. The current under steady state condition, current comes only from the first step, current for the Faradaic reaction, this reaction comes from the first step. Current for the capacitor will be there if you are applying an AC potential. If you apply DC potential, the metal solution interface, which you can visualize as a capacitor, if you apply DC potential, the capacitor will not pass any current under steady state condition. If you apply an AC potential, capacitor will pass current. In addition, applying AC potential will make this reaction go faster or slower. When the potential increases, it is going to go faster, when it decreases, it is going to go slower. If it is periodic, we expect the reaction to become faster and slower accordingly. So, if I say this is the rate constant value at a DC potential, this is the K1 DC. So, potential is DC up to some time, and then if you apply an AC, rate constant will also move up and down. Along with the movement of rate constant, the fractional surface coverage will also move up and down, that is theta will also move. Combination of theta and K1 together will tell us how the fractional surface coverage will move as per this equation. So, when we apply AC, we cannot neglect this and we cannot say d theta by dt is 0. When we have DC, when it is under steady state only, we can set this to 0. Under AC, we have to use the full equation.
Sir,
yeah.
Can you repeat what K1 into 1 minus theta represents? Is it the number of electrons transferred?
K1 into 1 minus theta tells the rate of the first reaction.
Yeah, like in units, what does it represent?
It is moles per square centimeters per second. K1 1 minus theta. Theta does not have units.
Okay, it is same as the chemical reaction.
Moles per centimeter square second. So, K1 1 minus theta represents the rate of the first reaction. Now, the first reaction gives 1 electron. Okay. I can have another reaction where M becomes M2 plus adsorbed plus 2 electron, and M2 plus adsorbed goes into solution. Copper can become copper 2 plus, copper 2 plus can go into solution. In that case, I will say rate of the first reaction consumes M surface at this rate of K1 1 minus theta, number of electrons produced is 2. Okay. This is still moles per square centimeter per second. Now, Faraday constant converts the electrons to coulombs, moles into coulombs. So, I had to multiply by F, which is Faraday constant, coulombs per mole of electron. So, in this case, because it is single electron transfer, I am not showing the number 1, multiply by this to tell how much current will come. It is going to be coulomb per square centimeter per second, coulomb per second will become amperes, amperes per centimeter square. So, although I say when I talk I say it is current, it is actually current density, it is not current.
So moles means it's electrons, not a surface atom. Number of surface atoms.
K1 1 minus theta is the number of surface atoms that are consumed. So, it is number of surface atoms that are consumed by the first step. It is also equal to the number of M plus adsorb produced by the first step. It is also equal to the number of electrons produced by the first.
In this case, it is like that, but in copper 2 plus case, so it is giving 2 electrons, right? One copper.
So, number of electrons will become 2 into that rate of the.
Here, the mole means moles of electrons, not moles of atoms. Is it like that?
No, here the K1 1 minus theta represents the number of M surface atoms that are consumed by the first reaction. Okay. Because you can look at this equation and say this equation gives 1 electron, therefore, it is equal to the number of electrons produced by this step. I do not know where the confusion is.
Okay, first we will write this equation in terms of
Surface atoms, and we calculate how many electrons are produced by that. If it is reversible, I would write K1 1 minus theta as a number of electrons produced by the first step, forward step. Reverse reaction I might write it as K minus 1 into theta, that tells number of electrons consumed. So, the net number of electrons produced are given by K1 1 minus theta minus K minus 1 into theta.
So, that is what I am when you are writing IF equation curve,
Yeah.
calculate the current, you need to write moles of electrons instead of writing moles of surface atoms.
Yes,
That is what I am.
yes, exactly. So, for example, here the second step does not produce or consume any electron, therefore, it is not at all showing up in this equation. Whereas, when you look at theta, theta equation first produces theta, therefore, it is positive number here. The second reaction consumes theta, therefore, it is a negative number there. So, we write the equation based on the reactants usually. We will say K1 1 minus theta represents the number of moles of M consumed, moles per unit area that is consumed. For electrons, we have to calculate as per the equation. First equation produces M plus adsorb. So, when I look at M plus adsorb balance, I will consider first equation and the second equation, because it is involved in both. When I look at electrons produced, I do not have to look at the second equation, because it is not at all there, only the first equation I have to look at. Okay. So, if I look at the steady state current, it is going to look like this. It is not really going to be valid at DC potential of 0, because at DC potential of 0, that is equilibrium, I will have reversible equation, but we will not worry about that now. We will say it is when it is little farther away from 0, it is in the positive direction, K1 will keep increasing with potential. Theta is going to increase with potential. When EDC is large, theta is going to be close to 1, 1 minus theta is going to be close to 0. And this expression F K1 DC 1 minus theta you can calculate from this. This is going to give you F K1 DC K2 divided by K1 DC plus K2, correct. this, when I take this into the numerator and do the algebra, and this I can divide by K1 K2 on the numerator and denominator. Correct. The numerator divide by K1 K2, the denominator divide by K1 K2, and when K1 DC is going to be a very large number, because I am going to very large DC potential, this term I can neglect it, it is going to remain a constant. So, the Faraday current is going to increase up to some level and then it is going to remain a constant, although we have assumed that mass transfer is not a problem. The signature, if you look at this, will look somewhat similar to a mass transfer limited case, even though mass transfer is rapid. Does it make sense? If you look at the current versus potential, when I go to intermediate level of potential, current increases with potential. When I go to large potential, current saturates. And if you have a simple reaction, which you have seen earlier, if I have a very simple reaction, when it is kinetic limited and mass transfer is very rapid, we know that it is going to give an exponential curve. We have seen that before, it is going to go like this. Whereas, when it is mass transfer limited, although we have not derived it, I showed you the example, it is going to go like this and saturate. So, when you look at the signature, you can't always immediately come to the conclusion that it is going to be reaction number 1 with mass transfer limitation, or it is going to be reaction number 2, which we are seeing now with large potential, even though there is no mass transfer limitation. Here what happens is, when you go to large potential, entire surface is covered by M adsorbed. K2 is not going to increase with potential, because it is independent of potential, there is no electron transfer. So, the rate of production of this species M plus solution is limited by this, it is saturating. You can't have any more of the first step, because it is already pretty much covered by M plus adsorbed. It is not 100% covered, it will never go to 0 current, it will go to a maximum current and remain there. So, this is steady state behavior. Everybody is comfortable with this? Will you be able to derive this? Okay. Now, the fun starts. Okay. When you go to AC, we use the notation that EAC is going to be AC0 sin omega t. We will vary the omega. We are going to assume EAC0 is small, and we know that we can write K1 as K10 e power B1 e, and in general we will write it as e power B1 e dc plus EAC, where EAC is EAC0 sin omega t, and in general we know we can write it as B1 e dc, and this can be approximated by 1 plus B1 EAC when EAC is small. EAC is small when EAC 0 is small, because sign can be between plus or minus 1. We have done this in the previous case. When you have simple electron transfer reaction, we said K forward. If I apply DC plus AC, I will write it as K forward DC multiplied by 1 plus B forward EAC. In this case, it is B1 EAC. K2 of course remains a constant, it is independent of the potential. Now, I want to write the Faraday current. When I apply a DC potential and superimpose an AC on top, I expect the current to also have an oscillation. I want to know what is the oscillation. So, I can write the current as DC current plus AC current. Then I can write the impedance, Faraday impedance, as EAC by IAC. So, I am really measuring the differential impedance. So, what I want to do is take the current, this is given for DC, I want to write it for AC and derive the expression for impedance. Now, in general the current is going to be F K1 1 minus theta, where K1 can be time varying, theta can be time varying. So, K1 I know how to approximate it, K1 DC into 1 plus B1 EAC when EAC is small. This theta also I know it is going to vary with time, because the rate constant K1 is varying with time, surface coverage also will vary with time. I have to find how that is going to vary. So, our goal is to find this is not a constant, this is going to vary. How is that varying? That is going to help me figure out how to write the IF as IFDC and IFAC. So, we have this expression, this is an approximation symbol. In general, surface coverage is going to vary with time, it is going to vary with potential. We are going to write it as Taylor series. Initially, surface coverage was at steady state value, DC potential was applied, then we start applying an AC potential. We will say deviate slightly from the DC value. Therefore, we will write theta as theta SS. So, it is like writing, if you have a function of x and you know the value at x 0, we can write x plus h if you know the value at some location, very close to that location it is going to vary a little and we are going to write like that. So, here theta is the function, we will write theta at steady state plus first derivative evaluated at x 0, here it is EDC, small change we are going to write it as EAC. It is still a variable, but we are going to just use the same formula here. EAC is not a constant, by the way, EAC is EAC 0 sin omega t. Then 2 factorial, second derivative EAC square and so on, it is going to have more derivatives. But since we say EAC is a small number, we can say EAC square and higher order numbers can be neglected. That means, we can write theta as approximately equal to theta steady state plus d theta by dE at EDC. So, I need to evaluate theta as a function of E. Surface coverage, how is that going to change with respect to potential? Which means I can go to the original current equation, please substitute and write this. So, originally this equation was f k1 1 minus theta. Instead of k1 we are writing it in Taylor series and then truncating. Instead of theta we are writing it in Taylor series and truncating. Now, I want you to do this, f k1 dc remains outside, this is one term here and another term here. Here I would like you to consider this as third term and this as fourth term. You have something like a plus b multiplied by c plus d. You are going to get AC, AD, BC plus BD, correct. 4 terms are going to come out of this. One is a constant, 1 minus theta is a constant. This depends on EAC, this depends on EAC. So, you will get 4 terms out of which one is going to be a constant, another is going to have EAC, third term is going to have EAC, fourth term will have EAC square. Please write that. And since we have neglected EAC square and higher order terms earlier, saying they are not significant, here also after getting the 4 terms you are going to throw away the 4th term and keep only 3 terms. Okay. Theta is going to vary with potential. How do you write a Taylor series for a f of x? Okay. This okay? And so on.
Like what is the functional value of d theta by dE?
We have to find that. I have not yet come to that. So, that is the next step. What we do here is to say, I want to write the current in terms of AC and DC components. In order to do that, I have to write any variable as Taylor series, truncate after the first term here meaning EAC is significant, but EAC square and cube and so on are negligible.
So what should be the order of the EAC value so that we can maybe?
Depends on the system. I will tell you practically how it is. If you measure at 10 millivolts for normal system, I am not talking about batteries and fuel cells where you usually use galvanostatic method for corrosion, for electrode deposition. If you are using 10 millivolts, nobody will complain. 10 millivolts of peak, 20 millivolts peak, you can probably get it accepted in most cases. 20 millivolt RMS, maybe. 50 millivolts, people will start complaining. 5 millivolts, nobody will complain, but your noise level may go, noise level meaning the signal to noise ratio may not be good. Noise level is going to remain at whatever level it's in. 1 millivolt, everybody will be happy, but will people start doubting the authenticity of your data if it looks really good. So, the correct answer is it depends, but that probably is not going to make you happy. 5 millivolt to 20 millivolts you can probably manage. I do not know if it is going to be linear at 20 millivolt. Okay. It may not be linear, but people will not question the assumption that you can approximate that as a linear response. If you want to know whether it is linear or not, you have to measure what are called as harmonics, and at 20 millivolts you will get some harmonics. You also have to measure, if I do it at 10 millivolts and if I do it 20 millivolts, if the impedance values are same in the entire frequency range, I can take that as a linear system. You have to do that, and you also have to measure the harmonics and show that they are below the noise level, then you can say this is linear, but it is going to take a lot of work. So, 10, 20 millivolts, 5 millivolts it is considered good. If you go to fuel cells, if you go to batteries, it is usually done in galvanostatic mode. That is a completely different story, meaning with whatever little evidence we have, if you apply a perturbation sine wave of 10 milliamps, 100 milliamps, 200 milliamps, you may get higher harmonics. But for whatever reason it appears that if I measure just the impedance, look at the potential perturbation and calculate the impedance, it does not seem to vary that much with increase in IAC 0. We do not know why, but that seems to be the one we have seen so far. So, there I do not have a real number to tell below this value it is really linear, above this value it is not linear. It looks like it is going to be linear in a large range, linear in the sense if I apply 100 milliamps or 200 milliamps per square centimeter of perturbation, I may get more or less same impedance, although the second, third harmonics are there to a significant level. Why it behaves that way I do not know yet. But coming back here to this, we are basically expanding K1 in Taylor series, we are expanding theta in Taylor series because we recognize that they are going to depend on potential. When potential varies with time, this is going to vary. Now, if I substitute it back here, I would get 4 terms here, right. F1 k dc is there. I will get 1 multiplied by 1 minus theta. I will get B1 EAC. So, I will have F1 K1 dc B1 EAC 1 minus theta, F1 K1 dc B1 EAC 1 minus theta. I will get F1 k dc constant here 1, this is going to be minus d theta by dE multiplied by EAC, and the fourth term is going to be this term multiplied by this term, which is going to give me, actually I think I missed the sign here, it is okay, minus d theta by dE B1 EAC, B1 is here, F1 k dc is there. Therefore, it is going to give me 4 terms, out of which the grayed out term I am going to throw it away because it has EAC square. Is everyone comfortable with this? So, would you be able to derive this? So, for this reaction with linearization, I can write the Faraday current as this. I am going to call this as the DC, DC meaning it depends only on DC potential, it does not depend on AC. This is the AC component, which of course depends on the DC potential as well as on the AC. Now, the only problem here is I do not know what d theta by dE is. Of course, I am going to tell you how to solve it, right, otherwise what is the point in showing you this. In order to get the d theta by dE, we need to look at the mass balance equation. Yes.
Theta naught is the steady state theta naught. Like
Yes, we are at DC. and then we apply AC. So, theta is going to vary away from the DC value.
So then in the Taylor series it should be EAC minus EDC.
See, the way we have written, E is the potential, okay, and that is EDC plus EAC. So, this is like x 0 plus h. So, h is representing the small deviation and x 0 is representing the DC level.
So theta naught is a DC level.
Yes, the way in fact we have written, if I remember correctly, is theta SS. Theta SS corresponds to theta at the DC potential of EDC. That is what we had told earlier, that theta SS can be derived at a steady state potential. Okay. Let us see if it is manageable. Now, this equation we have seen before. This is for unsteady state. For steady state, of course, we set d theta by dt to 0 and then get the values. Now, I want to write first the expression on the left hand side, d theta by dt. The theta varies because we are applying an AC potential. We know how the potential changes with time. So, I want to write it as d theta by dE, dE by dt. Now, how do I write dE by dt? There are a couple of ways. I would like you to look at this carefully. One, we can call dE by dt as this, where we say E is the sum of DC plus AC. Of course, DC when you take the derivative it goes to 0. AC when you take the, this is EAC 0 sin omega t, there is a small mistake here. It is DC plus EAC, which is written as EAC 0 sin omega t, and of course, the omega comes, sine becomes cosine. You are all familiar with this. I would write it as omega EAC 0 cos omega t, and this I can write it as omega EAC 0 sin omega t with a phase offset of pi by 2. Now, in a complex plane, if this is a vector, a phase offset of pi by 2 pushes it up, where this is real, this is imaginary. So, one way to write that is, if you multiply a number by j, it is causing rotation by 90 degree in the complex plane. If you give any complex number, multiply by j, where j is of course the square root of minus 1, it is going to be equivalent to rotating that with this origin as the center. So, I can write this expression as, take this value of sin omega t EAC 0 multiplied by omega, and then say that is equivalent to multiplying by j, and this expression I would get it as j omega EAC. This is another way to derive this. You can say E is EDC plus EAC 0 e power j omega t, where it is actually cos omega t plus j sin omega t. So, it is a complex representation of the potential. When I take the derivative of this, it is going to be j omega, this EDC is of course going to go away, it is going to be j omega multiplied by EAC 0 e power j omega t, which means j omega EAC. So, the point to note is d by dt in the complex notation that we write is going to be j omega EAC. Substitute it back here, you can write gamma d theta by dt as j omega EAC gamma d theta by dE. I would like you to be able to derive this properly, because everything else that follows depend on you doing this correctly. This and the next few steps, I will start with the next one and I will continue tomorrow. We have expanded the left side, we had to expand this, all these terms in Taylor series. Chop off the terms after EAC, EAC square and so on will throw away. Rearrange, we want to finally get an expression saying d theta by dE equal to something where everything on the right side is known to us. Then we can go and substitute it here. Okay. This is lengthy, but it is not very difficult. As long as you do the algebra correctly, as long as you expand these terms correctly, and as long as you recognize this part can be written as j omega gamma d theta by dE EAC, you will find that regardless of how many steps are there in a given mechanism, how many intermediate species are there, you will be able to write the impedance for all of these. It may need 10 pages of derivation, but it is not going to take anything more than writing in Taylor series, chopping off after some term, doing some algebra and recognizing this mass transfer equation, the left side of this mass transfer equation can be written like this. And of course, remember all these are applicable when we say mass transfer is very fast. This is a mass balance equation, right, not mass transfer equation. So, k1 1 minus theta minus k2 theta. I am going to write approximately as k1 I am going to write in Taylor series and chop off, 1 minus theta I am going to write in Taylor series and chop off. K2 is a constant, so I am not going to bother about that. Theta I have to write again in the same way. Get all the terms, keep the constant, keep the term with EAC, throw away the term with EAC square. In this case, you will not get anything beyond EAC square. Some cases you might get even more than that, you may get EAC cube if I have 3 products k2 theta 1 theta 2 in some expression, does not matter, keep only EAC and the constant terms. This we are going to keep the equation here, substitute it. For this we are going to substitute from here k1 1 minus theta minus k2 theta. I have shown it here, but I would like to actually do that and get it, because first time you may or may not get it correctly. I would like you to actually try that and get it. I will stop here now, but I will continue with this tomorrow, and then finally we will see the expression for Faraday current, write it as DC plus AC, we will get the expression for impedance, and then if you plot it, how will it look like in the Nyquist plot or complex plane plot. I will show you now how it will look like. After doing all this, it is going to look like 2 semicircles, possibly 2 semicircles. Depending on the DC potential, the radius or diameter of the semicircle will vary, but you can represent all of them by this Maxwell circuit or equivalent Voigt circuit or ladder circuit.